All right, so our next topic in chapter 6 then is going to be this idea of non-inertial reference frames. So the first question you might be asking yourself is, how are we dealing with non-inertial reference frames? What is an inertial reference frame in the first place? Obviously, there's only two types, right? Inertial and non-inertial. And so far, we've basically been dealing with inertial frames. And maybe haven't used this terminology before, but essentially, these inertial reference frames are reference frames. You can kind of summarize it as where our laws of physics behave as they normally do. It might sound a little bit more fancy or more complicated, but the main difference between inertial and non-inertial reference frames is that inertial reference frames are reference frames that are moving at some sort of constant velocity, right? Maybe that velocity is zero. We looked at this when we saw our unit on relative motion back in chapter 3. Um, Zero velocity is still a constant velocity, right? But you can say, okay, what's the difference between the reference frame looking at things from the ground or the reference frame looking at things from sitting still relative to this moving river or something like that. But the river was always moving at some sort of constant speed. Non-inertial frames then are reference frames that are accelerating, right? So if you have, let's say you're in your car, your car starts to accelerate. You have the ground outside is your inertial frame, and your car accelerating down the road, everything that's happening within that car is a non-inertial reference frame. Once it stops accelerating, once that car starts moving at a constant speed again, now you have your constant speed. You're back to what you're used to, and you have an inertial reference frame again. So the main difference between the two, I would say, is non-inertial frames are reference frames that are accelerating. And what we're going to see is that some interesting effects happen within these reference frames that are related to this kind of centripetal force that we've been looking at before. But for now, let's not worry about this circular motion at the moment. Let's just focus on some very simple non-inertial reference frames. And then we'll kind of come back and tie it into these circular motion problems that we had before. So let's imagine this. Let's do a little thought experiment. The simplest non-inertial reference frame that we can talk about that everyone has already experienced at some point or another is this one here. Let's say we are in an elevator, right? And this elevator right now is sitting still. So nothing interesting is happening. We're sitting in the elevator. It hasn't started to go anywhere yet. This right here would be our inertial reference frame, right? Our just regular everyday reference frame that we're used to. What are the forces acting on me and what do I experience in this sitting still elevator? Well, very simply, we have gravity pulling me down and we have the normal force from the floor pushing me up. How much do I weigh in this inertial reference frame? Well, it would be my regular weight, right? At this point, if we're sitting still, right, we can do our Newton's second law. You can say Fn equals mg, right? So the normal force is just equal to m times g. In my case, my weight is about 170 pounds. This is equivalent to, is about equal to 750 newtons, or this would be roughly equivalent to saying I have a mass of 77 kilograms. I don't want to say 170 pounds is equal to kilograms, right? That's not really true. Pounds are a force, newtons are a force, kilograms is a mass, right? So make sure you understand the distinction between that, right? This is how much stuff there is. This is the actual force generated by that mass, right? Due to the fact that I'm in this gravitational field. But so this is all very simple. This is all very normal, right? We've dealt with this stuff before. We're sitting in our inertial, non-accelerating elevator. It's just sitting still. If I weigh myself, I'll step on a scale, say about 170 pounds, or 750 newtons, whatever it happens to be. However, what happens when this elevator starts to accelerate? Say I press a button, I'm going up, and now our elevator starts to accelerate up. What changes about this picture? We're going to say it goes up with an acceleration of 1.2 meters per second squared. Now, what do I experience? What goes on within this non-inertial reference frame? Well, so again, from our Newton's second law perspective, this is a very simple problem, right? We have gravity pulling me down. We have the normal force pushing me up. We can write our Newton's second law. What do we get? We have Fn minus mg is equal to m times a, which we know in this case, we know that a is 1.2, right? Here's my individual forces. Here's my, some of the forces equal mass times acceleration. And we get this very simple equation, right? Nothing tricky here, but let's kind of take a look at some of the consequences of this. How else can I write this equation? Let's rearrange it like this. Why is that different, right? It's not really. It's the same equation. I've just moved over this ma. I've just subtracted over from both sides. However, there are some interesting implications when we write it like this, right? And really, you can kind of just think of it as looking at it from two different reference frames. This is what someone outside the elevator would see, right? The normal force is pushing up, gravity is pushing down, and this person in the elevator, in this case me, is accelerating straight up, right? So this is okay. But if we write it like this, we can imagine it from the perspective of someone inside the elevator. So within the elevator, right, what does this person know what's going on? Maybe they know, maybe they, of course, in real life, you hit the button, so you can say you're accelerating up. But within the elevator, what do you weigh on this scale? Let's say I step on the scale again. I've got my scale from last time, right? First time I stepped on it, it said I weighed 170 pounds. Now as I'm moving up, what does this scale say? Well, the scale, again, is just going to read the normal force of me standing on it, right? The normal force, it's basically measuring the normal force that the scale has to exert on me, right, to support my weight. And in this case, the normal force will be about 847 newtons, right? This, again, this would be equivalent to about 190 pounds. And so, as you can see, right, there's about a 20-pound difference between these two. Why does the scale read higher all of a sudden? Well, again, we know it's pushing me up like this, but you can imagine it this way, right? This is kind of one of these interesting effects within these non-inertial frames. Imagine, this is a very silly thought experiment that we can do, but you can kind of stick with me on this. Imagine someone was born in this elevator, right? And for their entire lives, this elevator was accelerating up at 1.2 meters per second. Would they be able to know, right? And they stepped on the scale now, they've grown up, they've lived their 30 years on Earth. They step on the scale and it reads 190 pounds. How would they know, how would they be able to tell from within this reference frame that there is any sort of difference between these two values here, right? That there's that this elevator is somehow not accelerating, or this elevator is, would they be able to tell basically the difference between this elevator accelerating at a constant rate versus sitting still in some sort of gravitational field? And the answer is that they wouldn't, right? There'd be nothing they could really do to figure out whether or not they weigh 170 pounds or 190 pounds. As far as they're concerned, it would just be 190, right? Within the elevator, within this non-inertial frame, as far as they're concerned, maybe they are still sitting still, but there is this extra force, right? So the effect that we have is, and you've all felt this before again on the elevator, when the elevator accelerates upward, you feel this extra force that pushes you down, right? And in this case, it's about 20 extra pounds of force. It's not quite 100 newtons worth, right? But when this elevator accelerates up, right, this acceleration up causes this extra force to appear to push you down to the bottom of the elevator, right? And so depending on which perspective you say, if you're outside the elevator, you can see it accelerating up. But if you're inside the elevator, you don't know, do you just weigh more, right? Or is it a result of this elevator moving up? Let's look at this again. But now let's say this elevator is accelerating down, right? So now I get to the top of my floor or whatever. And I need to go back down. I'm in this elevator, and now we'll say we're accelerating down, and with an acceleration still, right, of 1.2 meters per second. What does our equation look like this time? Now we have Fn minus mg equals minus ma, right? Here's my forces, here's my net force. And so, of course, I can rearrange this again. I can say the normal force then minus m times g times, let me rewrite this. The normal force minus m times g minus a equals 0. Now I step on the scale. And what does this scale read? Now it's going to measure a normal force of 662 newtons about, which again is roughly equal to 149 pounds. So now all of a sudden, again, you have the same situation, right? If for my entire life I had been in a reference frame that was accelerating down, right, I wouldn't have any way of knowing, right? So again, we have my mg this way, my normal force this way. But again, now I'm accelerating down, and what do I experience? I experience this kind of extra force that seems to be pushing me up and making me feel a little bit lighter. Again, you've all felt this. You get to the top of an elevator, right, and it stops, right? The elevator is still moving up, but it's slowing down, so it's accelerating downward. And you jump at the top of it, right? You seem like you jump really high in the air. And again, the reason you're able to feel like you're jumping really high in the air is because, again, for that time, while you're in this accelerating reference frame, you effectively weigh less, right? So within that frame, it looks like I mean, you can think of it two different ways, right? Either you are actually jumping really high in this reference frame, or it's really the elevator pulling away from you due to its own acceleration, right? Either way is totally valid, right? Any reference frame is completely valid. But again, the overall effect that you can observe, right? You can think about this as this extra force that seems to go in the opposite direction of the actual acceleration, right? So the book will call these fictitious forces. I don't really like that term because the effects of them are very real, right? So these happens with all sorts of accelerating reference frames. So what are other examples? Obviously, if we think back to our centripetal motion examples, we have our car going around a turn. If you've ever been in a car or in your friend's car or whatever, if they take a sharp turn to the left, or if you take a sharp turn to the left, which way do you get pushed in the car? You are turning left, you are accelerating to the left, and so you feel as though you are being pulled to the right side of the car, right? There's this extra force that seems to be pushing you out to the right, to the outside of this turn. If you've ever ridden the Metrolink, right, and it's sitting still, it's about to take off, and you just stand there and you don't hold on to anything, the train lurches forward and you might fall over backwards, right? The train is accelerating forward and you feel this extra force that pushes you backwards. As it turns out, these forces are something that are called gravity-like forces. So that's kind of one term. I don't think the book uses this term. The book uses the term fictitious forces. Again, I don't like that terminology. I know what they mean, right? It's kind of just a result of the motion. However, it's important to understand that the effects of these forces are very real, right? If you are in your car and you're driving along and you're not wearing your seatbelt because you're a big dummy, and you get into a car accident and you fly through the windshield, that's as far as the book was concerned, the book would label that as a fictitious force. But I promise you, flying through the windshield is a very real phenomenon, right? You're not going to think to yourself, oh, this is a fictitious happening or anything like that, right? It's a very real effect that these supposedly fictitious forces happen. That's why I kind of use the terminology like extra forces, right? So yeah, so when we have these accelerating reference frames, right, this acceleration appears to kind of create these extra forces that show up. So why did I say that they are gravity-like, right? So just so we all know what I'm saying, gravity-like forces appear in non-inertial frames, right? So if I accelerate forward, I get pushed back, right? Just think when you're in your car, right? You step on the gas, you feel like you're getting pushed back into the seat, right? The reason they're gravity-like is because they apply the same acceleration to all of the objects in the frame. They do not apply the same force, right? They apply the same effective acceleration. So I mean by that again, if you get in your car accident or whatever, you fly forward and you accelerate for a moment at 20 meters per second squared, right? And you have like a box of tissues in the passenger seat or something like that. I don't know, whatever, a book or a backpack, it doesn't matter. That stuff has much less mass than you, but it will also accelerate forward at the exact same rate. You have different masses, but you have the same acceleration, the rate of acceleration within these frames, which means the effective force that you're feeling, right, this effective strength of this extra force does change depending upon your mass. The acceleration is the same, so the strength of the force is different. And this, of course, is just how gravity behaves, right? objects within a gravitational frame, right? If I go outside and I can ignore air resistance and I drop my hammer and I drop my feather, they will fall at the same rate. The hammer and the feather both experience the same acceleration, just like you have within these accelerating frames, right? Let's look at kind of another more extreme example of this phenomenon, right? Let's say you're in your elevator, right? And something terrible happens. So we're in this elevator, and now, heaven forbid, you find yourself accelerating down with an acceleration of 9.8 meters per second squared. So what happened? Obviously, you're in the elevator, and if the cable were to snap, right, and the elevator were to start falling down the elevator shaft in free fall, it would fall at a rate of 9.8 meters per second squared, right? So now, in this case, hopefully this never actually happens to you, but if it does, you can do some fun physics as you plummet to your doom, right? So what would the normal force that you experience be in this case? So again, what are my forces? We have gravity pulling me down. We have our normal force pushing up. And how does this affect my Newton's second law equation? We have Fn minus mg equals minus mg, right? So in this case, I am accelerating down at 9.8 meters per second squared. And what is the magnitude of the force that I experience, the extra force? I am accelerating down, I experience an extra force up such that my weight actually cancels out. And this is what we call free fall, right? You're accelerating straight down along with gravity, right? Gravity is the only force acting on you. It is pulling you down. You're accelerating at 9.8 meters per second squared. The force that you experience essentially within this reference frame, the extra force accelerates you up at 9.8 meters per second squared, right? So you have gravity pulling you down, you have this extra force within this frame pulling you up, and within this frame, you are weightless, right? You are just floating around within this, right? There's nothing there to really, if you grab the scale and you push it up against yourself, then you'll measure something. But if you just try and stand on it, the scale won't read anything, right? There's not going to be any sort of force pushing you down into scale. You, the scale, everything else in this elevator are in free fall, falling down this elevator shaft, right? And so this is actually a very interesting consequence. How does this relate to some of the stuff that we've been doing also in this chapter? Well, so this is actually going to help us with our next section, going to kind of help us understand how orbits work. How does this elevator falling down the shaft help us understand how orbits work? Think of it this way. Ignore this stuff for now. We're going to come back to it in a second. Here is Earth. Let's say I am standing on Earth and I throw my ball. And it goes like that, right? We already know everything there is to know about projectile motion, right? We remember studying that a couple chapters ago. If I throw my ball, it takes a path that looks something like this. So this is how, and then if I throw it faster, what does it do after that? If I throw it even faster, it might go like this. So of course now you're going to have to suspend your disbelief here. We have I'm telling you I'm throwing this ball, several thousand miles across the surface of the Earth. But you can imagine, as I throw it faster and faster, it goes further and further. What happens if I throw this ball at just the right angle and at just the right speed? That would be the trajectory of that ball, right? So this is really all an orbit is. If you throw something at the right angle at the right speed, right, it's curving back towards the Earth. If you throw it too slowly, it curves back towards the Earth. If you throw it just at the right speed and just at the right angle, it will curve back towards the Earth, but it will never actually intersect with the surface of the Earth, and it will just keep going around and around, right? This is what the International Space Station is doing, right? Where you see those videos of the astronauts as they float around. Why are they floating? They are in free fall, right? Again, they are in an accelerating reference frame. So here's their little spaceship. It's moving along with some speed v. Which direction is the force acting on it? Well, gravity is pulling it straight towards the Earth, right? So these accelerating reference frames that we have here, right? In this case, we're accelerating straight down, we're moving straight down, our acceleration and our velocity happen to line up, but we experience this weightlessness. However, In this case, with a space station, as it orbits around the Earth, we launched it very, very fast. It's moving at about 17,000 miles per hour. That's how fast it needs to be moving in order to not, crash into the Earth. Um, and but the acceleration, the direction of the acceleration is the same as the direction of the force. The direction of the acceleration is straight in towards the Earth. The direction of their extra force that they experience is then going to be straight out away from the Earth. These astronauts are in free fall, right? And so when they're within this reference frame of the space station, they do experience this weightlessness, right? What the only force of gravity they experience would be the gravity that they experience between themselves and the space station, right? But the Earth's gravity is effectively canceled out by the fact that they are in free fall, right? Gravity is pulling them straight in. The effective extra force that they experience is pushing straight back out and canceling it out. So yeah, so that's just kind of a quick primer for these non-inertial reference frames, right? And kind of you can see some very interesting consequences of them, right? If you accelerate forward, you experience an extra force backwards. If you accelerate down, right, these astronauts in their space station, they're moving, right? They have a very high horizontal speed, so they're following this curved path, but the acceleration is still straight down, so they experience an extra force up, which is then why within their reference frame there is no, there's effectively no gravity, right? So this will kind of then lead us into our next section. We're going to talk a little bit more about gravity, and we're going to talk a little bit more about these orbits.